I'm Dave Seeloff, and today I'm going to be talking about advanced code analysis techniques, tips and tricks to develop more secure and reliable drivers. The reason why we're talking about this is because we know that customers want reliable products. But in order to deliver those reliable products, some of the bugs we have to deal with can be really tough to find by traditional testing and debugging techniques. And really, any time you can find potential crashes or other misbehavior earlier is really a good thing. So what I'm going to be doing today is introducing the Microsoft Source Code Annotation Language, SAL, and talking about Visual Studio Code Analysis, how to interpret the warnings and how to use it with SAL. I'll be walking through adding SAL to an existing driver. And hopefully what this will do is we'll add this technique as part of one of the tools you've got to help improve the reliability of your software. So Microsoft Source Code Annotation Language was something we designed to try and capture important aspects of the intention behind the code. You can think of it as like using asserts in a more structured way on function declarations and variable declarations in order to describe what's trying to do in a way that both humans and tools like code analysis can understand. And the two aspects of that I'm going to be talking about today, one is locking behavior. So this will enable us to help find potential race conditions and deadlocks, as well as parameter behavior, where we can help find potential null pointer dereferences and uninitialized memory use. So to give you a flavor of what that looks like, what kind of model we have for these annotations in the source code. So let's start with talking about locking behavior. So if you've got a function where, say, it's a wrapper for enter critical section, and maybe does some logging associated with that, you'd want to annotate that function with acquires lock to indicate to the caller that this lock has been acquired and it's now your responsibility to release it later on. Later on, if you've got a function that calls leave critical section and maybe does some more logging, you would then annotate that function with releases lock to tell the caller that after this point you can't count on holding that lock. If you've got a function that depends on a lock being held by the caller so that the callee can access shared memory without worrying about any kind of race conditions, you would annotate that function with requires lock held. And if you have a particular variable that you want to indicate as a shared variable that can only be accessed when you have acquired a certain lock, you would annotate that function declaration or that variable declaration with guarded by. So let's give a demonstration of what that means in the context of some real code trying to find potential race conditions and deadlocks using Visual Studio Code Analysis. So I have some driver code here. So this is code that maybe it's in development, hasn't been released yet, it's in testing, and we've got some potential concurrency issues we're dealing with, maybe hit some deadlocks in testing and some memory corruption on shared variables. So I've run Visual Studio Code Analysis on it without having added any SAL yet. Now, I'd just like to note this is the developer preview version of Visual Studio, and so there's going to be some warnings you may see that look like they're coming from Microsoft header files or from other places that don't make sense to you. And while there are some rough edges we're dealing with, so just for now, focus on the warnings that are clearly coming from your code, and you just deal with the ones that you care about. So like right now, I only care about this failing to release lock warning. It's saying that I'm failing to release this lock GCS sync. And if we scroll up a little bit, we see that we're leaving the critical section here. But if we go up further in the function, we do actually see that we enter it here, and there is a way that if this function call fails, we'll end up in this cleanup block down here with p-adapter details being null, and so we won't ever leave this critical section, so we could have a potential for a deadlock. So the right thing to do in this case is to make sure we move this leave critical section out of that if block. So the next thing I want to do is go to one of my shared variables, which is this GDW thread count. It's got the current count of the number of threads running, and I just want to indicate that it is guarded by this particular lock. And the relationship between GW thread count being guarded by that critical section is something that any developer working on this code has to know. In fact, many of the drivers that I've looked at, you actually have that in the comments somewhere, that you must acquire this lock before you touch this variable. So by putting it in so it's information that has to be known anyway, so if we just encode it in this way that's should be very readable, it makes it obvious to code analysis as well as developers what's going on. And so code analysis can now analyze our code. And what we found is that the original warning that we were looking at is no longer being discovered, so we're not seeing any potential for deadlock in that function anymore. But there's a couple of new warnings. This one says missing requires lock-held annotation or no competing thread in this function. Otherwise, it could be a race condition. And this is obviously because we've told it now that GDW thread count is protected by GCS sync. Now, this function I happen to know is one that does a lot of work for the for the threads that are running. So we don't want to hold this lock for the entire time that this function is running. Instead, all we need to do is grab the lock for the duration of the update. And that way there's no chance of stomping on someone else's decrement if two threads are leaving this at the same time. So the other warning, same warning text, but in this case it's a little bit different. We are clearly accessing this variable without holding this lock, but we're in DLL main, and we're being called for DLL process attach. Now the operating system guarantees that there's only going to be one thread running at a time when DLL process attach is called, so we don't have to worry about any race conditions. So we will use this no competing thread annotation here to mark the section of code where, excuse me, to mark the section of code where we don't have to worry about race conditions. So we could add the same thing if necessary to DLL process detach down here, but we wouldn't want to do it for the entire function because, of course, DLL thread attach, there could be competing threads, there could be race conditions to worry about. So this is, so now rerunning code analysis, and hopefully what we'll find is that it solved these particular problems. We added one annotation for this guarded by relationship, and it pointed out one warning. Now, you're rarely going to find one annotation points to one warning, but this speaks to the power of code analysis when you start giving it critical information about how your program is intended to run. So let's move back and now start talking about parameters. Now, when we designed SAL, we examined the common patterns of parameter usage and came up with 4 basic categories that cover the vast majority of cases of how people use parameters in practice. And we've got input parameters. This is where data is passed into a called function and treated as read-only, and some structured data that the function needs to operate on. Then you have input-output parameters. Similarly, it's passed in a nice structured way. The function is going to read from it, but it's potentially going to be modified. You have output parameters where all the caller is doing is providing space, and the called function is going to write into it and return some data that the caller then is going to use. And output pointers is really just a refinement of an output parameter, but where what's being returned by the called function is a pointer. And this is called out especially because there's some interesting additional refinements on output pointers that don't apply to regular output parameters. Then you've got those 4 basic categories, and we can refine those in various ways to provide a little more detail. So the most common one is whether it's required or optional. A required parameter is a pointer that can't be null in order for the function to be able to operate properly. If you pass in a null, the function might crash. It might return a bad status without having done anything useful. Generally can't do its job. An optional parameter is one where you can pass null and nothing bad happens. There are no bad effects whatsoever. The function can do its job as necessary. And we'll see examples of all this. And I just want to show you this table because this really demonstrates that how we construct annotations that you actually apply in practice to to parameters where it's all built up of these different concepts of whether it's in, out, so on, whether it's required or optional. So now I'm going to return to my code, and I'm going to start looking at other kinds of warnings. To begin with, I want to start again with a warning that was pre-existing. This was before I added any sal, and it's this one here, dereferencing null pointer. And this is an interesting one because it tells you, gives an example of what exactly code analysis is thinking as it's producing this warning. It walks you through its reasoning that on line 661, p adapter details might be null. You're checking for it here. And if you walk up earlier in the function, you find that yes, there is an error path where p adapter details at this point can be null. But then at 670, you're making this function call, and while we're evaluating the parameters, we find that there's no guard, and so it'll crash. So even though we tried to be safe earlier, we will not be safe here. So the right thing to do in this case is to put in a similar guard like above and prevent us from crashing in that particular error case. So the next thing I would do is then I would want to start annotating my code. So the way I would start is start with the low-level functions, the ones that sort of provide the basic services in your code base, and start annotating there, trying to make sure you get the semantics right. Make sure that they're really rock solid and reliable and well understood in terms of what they do. Then you build up from there. So we'll kind of see how that goes. So we'll start with this function, get new1xData. Its parameter is a pointer to pointer, this pp1xData. Now the first thing we do is we assert that it's not null. So clearly this is a required parameter. You can't call this function with a null. So let's, instead of making an assert that's buried in the function, let's put it right there in the function declaration. Then if we scroll through the function, we find we never read from it. We just write to it here, and we allocate some structure, and we fill in the fields, and then we return it through this output parameter. So this is a classic case of an out pointer. Moving along, we have free1xData, and its parameter is also a pointer to pointer, but in this case it checks for null, and then nothing bad happens if it is null, so it's an optional parameter. Here it reads from star pp1xData, and then it writes back to it. And so this is a case where it's an in-out, it's reading and writing, and it's optional. Now there's more you could say about what it does, but you don't need to provide every single bit of detail. You just start with this, and that's going to provide a lot of information for code analysis. So is 1x result params available? It takes a pointer parameter here, and all it does is read from it. It doesn't write to it anywhere. And the first read it does ends up checking to see if it's null, so you avoid reading, dereferencing it if it is null. So this is in, and it's optional. Free RC4 packet takes a pointer, checks to see if it's null, nothing bad happens if it's null. It reads from it, it writes to it, it's an in-out opt. Flush RC4 packet cache takes a pointer parameter, it asserts on it here, so again, this is a required parameter. You can't call this with a null, or else the program crashes. And then it passes the address of some of the fields of that are pointed to this free RC4 packet, which, as we said above, is an in-out, and since this is in-out, then this must be in-out as well, but this time it's not opt. And I'm just going to do one more here, this cache RC4 packet. And this is an interesting one, so let's take a look at each parameter in turn. So the first one, p1xData, the first use of it is down here where we dereference it without having checked. So this is not an optional parameter, it's required. It passes the address of this, of one of the fields, to this free RC4 packet, so therefore it's in-out and not opt. The next one is a ulong. Now this is an in, I'm going to call it an in. Scalars, you don't have to annotate them, but if you do put it, you just call it in. Scalars can only provide data as an input. You can't return any data via an input. This is a pass by value language. So I just like to annotate all the parameters just to make sure I don't miss any. So the last parameter, PBEAO packet, the name of it kind of gives you some intuition that maybe it's related to this uPacketLen parameter. So let's take a look and see. Now the first thing we see is that if PBEAO packet is null, then we're going to bail out of this function with an error code. So in other words, this is a non-optional parameter. If you call this function, you should pass in non-null. So then we take the packet len and you make a packet copy. Then you copy from the incoming packet into the copy with this length. We never end up touching that input parameter again. So it's just an in, and we read uPacketLen from it. And this is one of the ways to describe a buffer size. I'm not going to go into the variations on buffer size annotations. You can find information about that on the website where we describe SAL and code analysis. But what I really want to emphasize here is what we're doing is we're making very explicit this critical relationship between these two parameters that's implicit in the code. You've got to understand it, you've got to get it right in order to be able to work with this code effectively. And there we've run again, and so we've got some new warnings to take a look at. And the first one here, using uninitialized memory. So what this is saying on star pp1x data, what it's saying is that this annotation out pointer is saying that we're promising our callers that we're going to put a valid pointer into star pp1x data. And there's a way that we might not do that. And in fact, this error path, we aren't going to do that. So there's a couple ways we could approach that. One is we could say that we want a success annotation. And what this is saying is that the callers of getNew1x data have to check the return value of getNew1x data, and if it returns error success, then you can believe all the promises I made in my annotations. If the return value is something else, you can't trust that. And there's ways to specify what functions will do in the case of error, but I'm not going to get into that today. But actually, instead, the approach I'm going to take is use a variation on the out pointer annotation, where I'm saying that the result might be null. And to make sure that that's true, I'm going to initialize it to null here. That way, before I branch to any possible error paths, it's being set to null. It'll get reset to a non-null value if everything works well later on. The next warning here is saying that I have some nicely annotated function body, but a declaration that's not annotated. So what I need to do is, for that and for free1x data, I need to copy the annotations over, and the warning itself tells me exactly where the declarations are that need to have the annotations. The reason why this is important is because code analysis, as we've seen, it's speedy. It's fast enough we can use it repeatedly during the course of this talk. And one of the ways that we do that is we look at one function at a time. So as code analysis is looking at one function, it looks at the SAL it can find on the declarations for the functions that are called. So if it finds a declaration that has SAL, it can do a better job of analyzing the code and give you more relevant results. If there's no SAL in the declaration or can't find a declaration, then it's going to give you less accurate results, it'll give you less value. So as we see, those warnings have gone, and we've done a good job of annotating some of the base layer utilities in this driver, and we can feel good about it because it's going to live with the code, it's going to be checked all the time whenever code analysis gets run. So now kind of switching gears, let's say that maybe I'm a new developer working on this project, and I've been assigned to fix a bug, a crash that has been discovered at this line here, line 503, and when we look at the crash dump, we see, hey, p-adapter details, arrow p1x data is null. So what I might want to try as a fix is just make sure that it is not null before I dereference it, and before I try and make this call where I dereference that pointer, while evaluating the parameters. And then I would have to build and deploy the driver and start my test pass to validate the fix. Now with Visual Studio Code Analysis, what I'll do is I will run code analysis on it before I start that process, just to make sure that there's nothing new that came up in terms of the fix that I just tried to make. And again, it's speedy enough that you may not want to do it on every single build, but it's certainly fast enough to do prior to your test pass. So we've got a new warning here, invalid parameter value. And it's saying that cache RC4 packet, which remember we just annotated a few minutes ago, said that the first parameter is not optional. It will crash if you pass in a null here. And the change we made said, hey, if p_adapter_details arrow p1x data is null, that's a very serious concern here, and we're pushing that down into the else clause. So we haven't fixed any problem at all. We've just changed where the crash is going to happen. And if this happened as a result of a test case in our test pass, then I would just find that out in testing. This is still faster than that. However, if this, say, was a crash report that we got from a customer and we don't have a way to repro the problem in-house, then I haven't really made any progress at all because the problem is still going to be there. It'll just have moved slightly. So just to recap, Visual Studio Code Analysis and SAL together are very powerful tools for you as a way to complement your existing testing infrastructure. Code analysis can find valuable bugs for you right out of the box, but when you start adding SAL, it makes code analysis even smarter and more effective. And if you look at this being a compile time assert system, I think that really helps set the context for what it is we're trying to accomplish. And you don't have to annotate your code all at once. You just start where it makes sense, and you move from there, and you may get some initial value, and you certainly will get incremental value as your code evolves and matures and changes over time. And there's a lot more information on driver development tools and certainly on Visual Studio Code Analysis and SAL available on our website. And thank you for your attention.